Okay, the final thing we're going to be looking at in this section is interest rates. And really how we're dealing with interest rates, it's an algebraic approach once we're actually doing the problem. But we're going to see how we can derive our interest rate formulas using calculus, okay? So that's what we're doing in this little section. So let's remind ourselves again from algebra, if we're compounding interest, either on a credit card or a loan or something like that, n times a year, we have the following formula. So A sub t is our new amount, and it's equal to our initial balance, A naught, times 1 plus our interest rate, divided by however many times we're compounding a year. Normally it's a monthly compound, right? Like your credit card and your student loans, the interest is compounded 12 times a year. All right, and then raised to the n times t. So let's talk about what all these variables mean. Again, I kind of mentioned it. So A naught, A0, is the initial balance. R is the annual interest rate. N is how many times we're compounding each year. So you can compound weekly, daily, monthly, quarterly, stuff like that. So how many times it's compounded per year. Okay, and T is time. And then last thing, A of t, what the actual function is, it's the new balance. So after we applied the interest, okay? So just a really quick review. Let's say you have like $100. That would be like your initial balance. And then, let's say you borrowed $100 and it was 5% interest. And so after a year, we'll do annual interest. After a year, you would have $5 in interest. And so your new balance is now $105, right? And so now when you go into year 2, not only is the 5% interest going to be applied to the $100, it's also going to be applied to the new interest. So your new balance is going to be 5% of this 105 and then add it on. And then, we do that forever until you pay back your loan. Okay, so that's how our interest is working. So ... Very, very brief example. Okay, so that's if we're compounding n times a year. We also talked about continuous compounding. So that means every single moment your account is gathering interest. And really, if we wanted to give this a calculus twist, it means that n, how many times a year are we going to be compounding? Well, if it's every single moment, we'll be compounding infinitely many times during the year. So really, we're talking about a limit when we're talking about continuous compounding. So in that case, A sub t would be equal to the following. We'd be looking at the limit as n approaches infinity of our formula we just had. The one we just wrote down for compounding n times a year. Okay, so that's what continuous compounding is. So let's clean this up. We're going to get a formula for continuous compounding. In algebra, you just kind of waved our hands. We waved our hands and said, ta-da, here's the formula for continuous compounding. And now in calculus, we can prove it. So let's see how we're going to do that. So the limit just involves n. So if a factor doesn't have an n, we can move it to the outside. So let's do that for the a naught. Okay, and then we'll rewrite all this. And then we're going to do a little bit of algebra magic on our exponent. Put a little space, and what we're going to do is we're going to divide by r and multiply by r. Okay, so it's all balanced, so nothing we're doing is illegal. And why we're going to do that is we're going to mess with our exponent rules. And we know if we multiply our exponents, it means we're raising something. We're raising an exponent to an exponent. So here, I'll write it out right here. So here's the rule we're using, but we're going backwards. If we're raising an exponent to an exponent, we're just multiplying the exponents. So we're going that direction. Okay, and then raise that to the exponent RT. Okay, so that's that step right there. Okay, and then what we're going to do, if that wasn't tricky enough, we're going to let m, and you'll see where we're going with this and why we're making all these crazy substitutions. We're going to let m be equal to n over r. Okay, so n over r, that means this is going to become m. And then that's, if r over n is the reciprocal of m, right? R over n is the reciprocal. It's backwards. So we're going to make both those substitutions, okay? So now continuous compounding, right, is now equal to this. 1 plus 1 over m raised to the m raised to the RT. All right, and then why are we doing this? Well, first, let me do one more thing. I want to use one more limit law. We saw that instead of just taking the exponent of a function and taking the limit, this isn't dependent on n or anything. So we can take the limit of, or the exponent including the limit. That was one of our limit laws from chapter 2. All right, and then also up here, because we have n, but now we have m. I should have changed it right here. But if n is going to infinity, right, divided by some small number r, if n goes to infinity, what's m going to do? Also go to infinity. So that's a pretty easy substitution. If n goes to infinity, because it's n over r, m is also going to go to infinity. Okay, lots of things here. Okay, but again, there's a purpose. And nothing we've done is illegal. Everything is either, an exponent rule or it's backed by a limit law. Does anybody recognize, whoops, this expression? That's the definition of E. That's the definition of E. So that's why we were doing all that weird, crazy manipulation. So now for compounding continuously, it's going to be equal to this. A sub 0 times E, because that whole thing cancels to E, raised to the RT. Oops. There you go. Okay. And then if that's the case, so that's how we're going to be compounding continuously. And then we can look at the derivative with respect to t. And it's the chain rule. So what would we have? Let's see. We can deal with that at the end. Outside function is e to the RT. Derivative of the inside function is just r. Okay. So we're looking at, do you guys see what's happening? What's this? that is just a sub t, right? So this is really, the derivative is really r times a sub t. Okay, so it's the rate at which our new amount is changing is proportional to the original amount. Okay, so again, really similar to the stuff we've been looking at before. Okay, so that's our calculus approach. We're finally able to prove the formula for compounding continuously. Let's practice using our formula in our final example for this section. Where are we going? We're going to number 22. So we want to know, how long will it take an investment to double in value if the interest rate is 6% compounded continuously? Okay, so you'll notice now that we've derived the formula, we're just going to use algebra. Okay, so let's say, I'm in my car. We have our formula. It's always nice to write out the formula once you realize the situation we're in. Okay, and they're talking about compounding continuously and rates, so we're just, that's the one we're going to use. And they're telling us that our original amount is going to double, or when is the original amount going to double with 6% interest compounding continuously? Well, if this is our original amount, this is our interest rate, what would double our original amount be? Twice that, so 2 times a naught. And now this is just an exponential equation we have to solve. So let's isolate this expression. So divide out by a naught. They actually cancel. Okay. And then we'll take the natural log of both sides. And we do that so we can bring down that exponent. And what's the natural log of e? It's 1. All right. Final step. Let's divide by 0.06. And that's going to give us the time it will take to double, our initial investment. And we'll get that t is, throwing it into our calculator, 11.5, and then what are the units? That 6% is an annual interest rate, so this is going to be in terms of years, since annual is 1 year. Okay, so again, very algebraic using that formula. Let's see what the last part is. What is the equivalent annual interest rate? Okay, so if it's an annual interest rate, that means it's not compounded continuously, it's compounded once. Okay, so, wait, what's the question? What is the equivalent annual interest rate? So we have this formula. Okay, and what do we know about it? We want to make sure it's doubled, so it's going to be equal to 2a naught. What's n in this case, if we're just doing an annual interest rate? N is 1. Okay, and how long did it take to double using a continuous model? 11.5 years. So let's have that be our t. Okay. All right, so this is a different type of exponential problem, but our variable is in the base. So let's see how we do it. So again, we are going to isolate this problem, divide out by a naught. Okay, and then we can take the nth root, so we can cancel that out. We can essentially like take the 11.5 root, but normally roots are integers. So alternatively, what we can do is we can multiply by the reciprocal, right, of 11.5, and that's like taking that side to the 1 over 11.5 power. Okay, and then we can do the same thing to the other side. All right, and the reason why we do that is because this, when we multiply it, will cancel out to 1, right? And so we'll have 1 plus r. Oops. And then all we have to do to solve for r is subtract that 1, and then we'll have our equivalent annual interest rate if we had to compound once a year versus continuously throughout the year. All right, so I'll let you guys finish that up, throw that in your calculator, see what you get, and that's the end of section 3.8.